or shrinking. This is a very useful transformation for trigonometric functions, but trig is not part of this course. So I'm just going to say that if we replace x by twice x or by 1/2 x, what would you expect to happen? So I have a function, let's say I have f of x, which is x to the third. We know this function, we graphed it. Anyone remembers when we graphed this function, x to the third? When we discussed or presented? No, this is not a parabola, it's degree 3. Parabola must be degree 2. When did we see this function? When we talked about odd functions. It should be in your notes. This is an odd function, symmetric with respect to the origin. Okay, so if I replace x by twice x, or I replace x by 1/2 x, like always, let's establish what type of transformation is it. Sandra, any questions? Go ahead, please. Okay, what type of transformation is it? Is it a transformation in x, or is it a transformation in y? When I replace x by twice x, or respectively 1/2 x. Is it a transformation or a change in x or a change in y? Of course, of course. And we also see this here. Because every time we're talking about something horizontal, obviously x changes. When we talk about something vertical, obviously y changes. Perfect. And what would you expect? Would you expect that when we change x into twice x, so one more time, x equals 2 to 4, right? X equals 2, when x equals 2, this will become 4. So what type of transformation do you think will that be? When I change x into twice x. Is it a horizontal stretching or a horizontal shrinking of the graph? That's what we would have expected. It's the opposite. That's the reason why I left this one alone till the last, as being the last transformation. Nope, it's exactly the opposite. Here's why. Here's why. So if I replace x in this function by twice x, then I have 2x to the third, and this becomes 2 to the third, which is 8 times x cubed. Now forget where this function was coming from. If you compare x to the third to 8x to the third, what transformation will this be? Is it still on x or on y? X cubed, 1x cubed, 8x cubed. Is it a transformation on x or on y? Right. So, I know it's a little bit confusing. Here's what I'm saying. This is x cubed. But 8x cubed is this or is this? Number one, x cubed. 8x cubed is this or 8x cubed is this? Number one or number two? Exactly. That's why when we change x into twice x, we would have expected this, but exactly the opposite happened. So this is a horizontal, not stretching, but shrinking. This one will be stretching. I just did not want to include this with all the other ones because this one is the only one that is completely opposite of what we would have expected. I think I'm fine with that. As I said, I'm not going to put any more problems or a problem like that on the test or the final exam. Only because it's slightly confusing. Okay, 2.6. Almost everything in 2.6 is a review, so we can go through it. I will not consider it a review. I will show you everything. So 2.6 in your book, it says combinations of functions, composite function. I prefer to call it algebra algebra of functions and function composition. So if we're given two functions, let's say f of x, simple situation, f of x equals x squared plus 1, and let's say g of x equals 2x minus 3. We can create a new function by adding them, by subtracting them, by multiplying them, and by dividing them. Each and every function we create will have a very clear name. What is the clear name? And I'm going to write it, and you're going to say, oh, I know, f plus g of x. What am I really telling you to do with f and g? I'm telling you to. Very good. F of x plus g of x. And I have x squared plus 1 plus 2x minus 3. That's all I'm doing. The function is called f plus g of x, or the sum of f and g. I will combine. Remember the keywords: combine, simplify, descending order, no negative leading coefficient, right? So we have x squared plus 2x minus 2. What is this? The sum of the given functions. What do you think I'm going to create next? Very good, awesome. Indeed, f of x minus g of x. Notice the notation, f minus g parentheses of x. F minus g of x. I'll copy x squared plus 1, but subtract. If you don't want to distribute at once, just put parentheses and distribute later. So this is x squared plus 1 minus 2x plus 3. We're just distributing inside parentheses. I will combine like terms, descending order, x squared minus 2x plus 4. This is a new function that was created by the difference of those two. Any questions?
And it's different because you use additional and subtraction.
They are new functions. So I obtain a new function, a new function, a new function, a new function. Every time I change the operation between f and g, very good question actually, I create a new function. So now I want fg of x. What does that mean, and what am I asked to do now? Correct, very good. So then I have f of x times g of x, and I write x squared plus 1 times 2x minus 3. Yes, I have to distribute. There are two binomials, and I've learned how to distribute a long time ago. Let's distribute. It doesn't matter how you want to distribute. You can distribute x squared to these two, and then 1 to these two, or 2x to these two, and then negative 3 to those two. It's up to you. I prefer this way this time. It doesn't matter. 2x to the third plus 2x minus 3x squared minus 3. In descending order, 2x cubed minus 3x squared plus 2x minus 3. And this is a new function determined by multiplying the given functions. Yes, Sandra, you want to say something?
No, I'm just.
So now, the last possibility is when we divide. So what do you think about this function? What will this be? So f of x over g of x. However, here I have to put if. I didn't need to put if on the other three, but here I have no choice. I have to put if y. Very good, awesome, thank you, Danny. G of x cannot be 0. So we replace those functions. So f over g of x, let's write it one more time, over g of x. So x squared plus 1 over 2x minus 3. We know we can simplify, but here I have to write if x does not equal. Can anyone give us the restriction of this function? We've seen something like this at the very beginning of the course. Rational functions. Which one? This is 2x minus 3. So 2 times 3 minus 3 will not be 0. Excellent. You have to set this equal to 0, right? Move 3 and divide by 2. Any questions?
So it's just adding 3 to both sides.
You have to write 2x minus 3 does not equal 0. 2x does not equal 3. X does not equal 3 halves.
And you don't do anything with the x part of this one.
But why would I?
I don't know.
But when is a fraction undefined? When the numerator is 0 or when the denominator is 0? It's a very good question. Because if we don't remember this, we need to address it. Say it again.
When the denominator.
That's it. I'm done. The numerator is free to be anything it desires. There's never a problem with the numerator. The only concern I have, division by 0. Can I divide 0 by anything? Yes, not by 0 though. So the only problem is division by 0. So that's why we wrote here, if g does not equal 0. We did not specify anything about f, because f can be anything. Is that clear, everyone?
Yeah.
Yes?
Yeah.
Perfect. Okay, now what is the potential problem here? Potential problem. So I want to add, subtract, multiply, divide functions. And you can say potential problem, I already know one. You cannot create a division if the denominator is 0. So that's a potential problem. But the other potential problem that I'm really talking about is domain, which is called common domain. What does this mean? What does this mean, common domain? So let's take a look. Let's say I have this function. Let's close it here. Let's say between negative 5 and positive 10. This is function f. And I'm going to draw another function. Let's say this function. Function g, between 1 and 12. And I'm going to ask you, let's find f plus g of 11. You will say, oh, this is easy. It's f of 11 plus g of 11, because that's what we just did. F plus g of x is f of x plus g of x. So if x is 11, then all I have to do is find f of 11 and g of 11 and add them up, and I get an answer. So I look at 11, which is here. I draw a vertical line through x equals 11. I see it hits the graph of g, and I read the y value, whatever you want, 10. So this will be 10. But now I'm asking you, how much is f of 11? And you will say, exactly. Why would you say undefined? It's because the domain of function f is very good, with a parenthesis, to 10. So no one can force you, because you can plug in 11 in this function if its domain is negative 5 to 10. So looking at those two graphs, what would you say to me? You will say, if you want me to evaluate any of those functions, you'd better choose an x where? You'd better choose an x. Say it again.
On the positive side?
Not, but 11 is on the positive side as well. So look at those two graphs and say, if you want me to evaluate or if you want to create these functions, you have to say, or choose a number Where? What do you think? Say it again. Why would it be 1 to 10? That's where the common domain is, where it's exactly where they both exist at the same time. Between 1 and 10, both functions exist. I will have no difficulties in creating the sum, difference, product, and ratio. That is called, what do you think? Exactly. So the common domain is 1 to 10. That will be the domain of 3 functions: the sum, the difference, and the product. How come that it's not going to be always the domain of the ratio as well? Because G could be 0. So in this case, since G is never 0, it will be the domain of all of them. But this is always, the common domain is always the domain of the sum, difference, and product. And I will say sometimes, not always, also the domain of the ratio. So what is the result or the conclusion here? If two functions do not have what? If two functions do not have a common domain, there's no way I can create a sum, difference, product, and ratio. They don't exist. Okay, so the common domain is crucial. So let's look at an example on page 310. Like 36, we are given f of x, which is 6x squared minus x minus 1, and g of x, which is x minus 1. They want everything and the domain of all of them. They want us to find the sum, difference, product, ratio, and the domain of all of them. Forgive me, 310, sorry. And now the question is, like with all the transformations and everything, the transformations were to be able to recognize patterns. Why do we do this? It's because, for example, here's an example of a addition or subtraction of functions. Let's say there are chain restaurants all over the world. Let's say the profit function of one restaurant is F1. The profit function on another restaurant is F2. The profit function of a third restaurant is F3. But the entire company would like to know what the profit is. So they will add up function 1 to function 2 to function 3 to get the total. So that's an example of adding functions. So here they want us to determine the sum, difference, product, ratio. So first let's find the domain of function f. Then let's find the domain of function g. And then let's find a common domain. And then we'll determine the rest, because we have to determine the domain. Can anyone give us a domain of function f? What can you plug in f? What kind of values? What do you think? What will be the domain of this function? Of course, it's a polynomial function, quadratic. It's defined everywhere. What about the g of x? Same. It's a linear function defined everywhere. What will be the common domain where they both exist at the same time? Luckily, it's everything. Good. No problems. So this common domain will always be the domain, always, of which 3 functions? The domain of the sum, very good. The domain of the, very good. And the domain of the, very good. Always, forever, for any 2 functions. The common domain. The common domain doesn't have to be this, but whatever it is, will be also the domain of the sum, difference, and product. Very good. So I don't have to write it again. Now, you're going to ask, what about the domain of the ratio? I don't know yet. Not yet. Okay? Good. So let's find the sum. So f plus g of x. I have to write the definition first. Please do not jump ahead. I know you can, and you'll get full credit from me, but please write the definition so you don't forget what it means, and then copy them. 6x squared minus x minus 1 plus x minus 1. I copied f of x. I added g of x. I have to combine like terms. I get 6x squared minus 2x minus 2. Sorry. Very good. Thank you. Sorry about that. Good. So now let's look at the difference. Same thing, but I will have to put minus, and I will have to distribute, -1. So f minus g, by definition, is f of x minus g of x. And then I copy 6x squared minus x minus 1 minus x plus 1. We have to distribute. I'm sorry?
Oh, you doing subtraction.
Is that okay, everyone? Okay, so now these two go away. So the answer is 6x squared minus 2x. Let's see the product. By definition, f of x times g of x. Please write it like that first as the definition, and only then replace. Put parentheses, please. 6x squared minus x minus 1 and x minus 1. And then I recommend distributing x to these three terms and then -1. 6x to the third minus x squared minus x minus 6x squared plus x plus 1. Combine like terms and descending order. Minus 7x squared. Now these two go away, and plus 1. What does this function represent? It represents the product of the given functions. I don't have to write the common domain again. It's clear. All these functions have the same domain with the common domain. So finally, we want to determine the ratio. Let's stop, and please ask any questions if you have anything for me, please.
So every time you have to do addition, subtraction, and multiplication?
Depending on what the problem is asking. You may be asked just to find the difference in the product.
Oh, okay.
You may be asked to present just the sum and the quotient. It depends. They may ask you f over g or g over f. It depends on the problem. But this one was asking us to find all of them. So then I would write f of x divided by g of x, which is 6x squared minus x minus 1, divided by x minus 1. However, here we may run into a problem. What is the problem we may run into? Excellent. So therefore, the domain of f over g from the common domain where they both exist, I must exclude which value of x? Which value? Exactly 1. So the domain of the ratio then will be -∞1 union 1 to infinity. From the common domain, we had to exclude the possibility of getting 0 in the denominator because this one was a ratio. Any questions? Any questions from you here, please? Yes?
I know you just said it, but can you explain?
I would like to say it again.
Can you explain again why x can't equal?
Very good. Can anyone say anything? Why x can? And if x is 1, then the denominator is 0. The reason I encourage you to say something or teach each other is because when you teach somebody else, then it really, really sticks in there. Is that clear? Priscilla?
Yeah.
Okay, perfect. So now there is a fifth way of creating new functions. Here's the fifth way. Totally different. None of the above. It's called function composition. For those of you, especially for those of you who move on to calculus from here, from this class, you must understand this concept. Function composition is not adding, subtracting, multiplying, or dividing. So let's take a look. 3 bubbles. I start with x right here, a number, whatever. And let's say I apply g of x to it. Or just g, maybe it's the same thing. But we normally just write g, not g of x. What do I get? Again, we come back to the same very important concept from a long time ago. We have a function, and I'm telling you x is 5. How do you find the y value? I'm giving you g is a function, and I'm saying x is 5. Find the y value. What would you do? Priscilla? Okay. Yeah. I don't like to put anyone on the spot. So we have a function, x squared plus 1, and I'm telling you x is 5. Find the y value. What would you do? Okay.
Or is it just one?
Okay, no. This is very important. We discussed this several times, but let's do it again. So let's say I have g of x, which is x squared plus 1, and I'm telling you x equals 5. Maybe because it wasn't written, it was not clear what I was trying. Of course. So then I find g of 5. Excellent. That's, if you said that, I apologize. I'm sorry I did. You said multiply, but this is not multiply. G of 5 is not multiply. This says find the function when x is 5. G of 5, not multiplication. This is not multiplication. It's the function g evaluated when x is 5, so which means 5 squared plus 1, which is 26. Okay? Good. So we apply g to a number. What do we get then? In lieu of what we just discussed, what do we get? If this is 5, you will say g of 5. But I'm telling you now in general, this is x. G of x. Good. This is a number now. And let's say we apply another function to this new number. So in my example, this was 5, and this was 26, right? 25 plus 1. So now I apply f to this number. But disregard the numbers. I want the general case. So what do we get now after we apply f to g of x? We get f of g of x, indeed. F of g of x. This is function composition. We plugged in a function, another function. So f comp g of x. That's how we read it. F comp g. The composite of f and g. So we created a new function not by adding two functions, not by subtracting, multiplying, or dividing, but by inserting in a function another one. Okay. Can you tell me what f comp g of x is or equals to? What would you say? F of x, indeed. F of g of x. Can anyone decompose this into an inner function and outer? What do I mean by inner and outer? I mean which function I apply first to x and which function will follow. And you can say, you already have it right here. Yes, but I want you to say it. So f of g of x. We always start from the inner to the outer. So what is the inner function? Indeed, awesome. And what is the outer function? Indeed. Inner by meaning we will apply it first, and that's what we did. We applied g first to x, and then to this number we applied f to get this. Okay. If I say, here's a function h of x, the square root of x squared plus 1. Please create, there is more than one correct answer here. Come up with an inner and an outer for us. Some function that we will have to evaluate first, and once we get a number, then we apply the second function to it. What will be the inner? Say it again. Very good. Once I'm done with this and I get a number, one single number, what function do I apply to this single number? Very good. So this is function decomposition. So now let's see how we compose functions. Okay, let me give you one more because this is very important. 1 divided by x squared minus 4. I would like you to create an inner. There is more than one correct answer. And an outer. I would like you to say, if you give me x equals 15, I will perform this operation first. And when I'm done and I get one number, then I will apply this operation, or I will do this with the answer. Inner function, please. Right. Once I get one number, I only have one number now. So what will be the outer? That's it. Very good. So, okay, you can say you showed us how to decompose it, but you haven't shown us how to compose it. This was function decomposition, yes, into inner and outer. So now let's look at an example in which we are given f of x and g of x. And we will look at function composition on page 310. Let's say, I don't like any of these. But anyway, so let's look at 54. 310. We are given f of x, which is 5x plus 2, but they are good enough. And 3x minus 4. They want us to find the following. They want f comp g of x. They want g comp f of x. Which is the inner function in g comp f? F of x is the first one. So f is applied first, and then g is applied second. So f will be the inner, g will be the outer. Here g is the inner, f is the outer. Okay, so they want f comp g of 2. And they also want g comp f of 2. Okay. First of all, I have to determine f comp g of x. What is the definition? Please always write the definition so you don't make a mistake. What does this equal to? F comp g. So this is f of g of x. Awesome. Do not erase it like this. I'm making a point. I have to replace the inner function first. Can anyone give us the inner function? Very good. But now, oops, 3x minus 4. But now I have to remember what to do next. F applied to 3x minus 4. What does F say to us? F says 5 times whatever you want plus 2. 5 times whatever you want plus 2. But my whatever I want now is 3x minus 4. So can anyone dictate what to write? 5 parentheses. Very good. 5, 3x minus 4, and plus. Awesome. Of course, I'll distribute. 15x minus 20, and plus 2, 15x minus 18. What does this represent? Is the function composition f comp g for the two given functions. Since I have this function, I just determined it. Can I determine this? Can I find this? Yes, I have the function. So then f comp g of 2 will be, can anyone dictate? 15 times 2 minus? Very good. So 30 minus 18, 12. Now I would like to look at G comp F. G comp F. What is it? This definition? It's G of f of x. I start with the inner. Do not erase it. I'm just making a point. So what is the inner function now? Very good. And now I look at G. G says 3 times whatever you want and minus 4. So can anyone dictate? Yes, parentheses. 5x plus 2 minus 4. We distribute 15x plus 6 minus 4, 15x plus 2. I have the function. I'm asked to find G comp f of 2. What should I do to the function I just created or determined? To find G comp f of 2. Plug in 2. Very good. So G comp f of 2 is 15 times 2 plus 2, 32. And that's how we create function composition. That's final. Yep. No, the function is this, and the value of the function at 2 is this. Now, do you remember a few minutes ago when we looked at the sum difference product, blah, blah, blah? I said potential problem. What is it? Right. There was no discussion of common domain here whatsoever. The functions do not have to have a common domain in order to create the function composition. But there is a much bigger problem here. Potential problem. I will not test you on this. I do with my pre-calculus and calculus, but not in this class. But I just, yes? Function composition. Yes. Say it again.
And you're not putting that on the test.
This potential problem. Yes. Everything else, yes. Yes. What could be the potential problem here? Let's go back to the drawing board, to our bubbles. I will not ask you this. Okay? So I have x, and I'm applying g. What do I get again? Excellent, g of x. And to this number, I apply f. What will I get? F of g of x. Awesome. Good. Can anyone tell us what does this set represent for g? What is this called? The set of all x values for g. What is its name? We use it all the time. When we graph, that's the start. Very good, awesome. Of course. Domain of G. Excellent. Great job. Now, what about this set for G? What does this set represent for G? What is it? True, but I haven't gotten there. You mean to F? No. What is this set for G? It cannot be domain, but it will be excellent. Range. Awesome. Range of G. Okay, also, what does this set represent for F? What is this set of values for F? What is it? Exactly. Domain of F. So what could be the problem? The range of G doesn't work well with a domain of F. So imagine G is applied to a number, and I get here G of 10 equals 3, but I cannot apply F to 3. We will never get here. So this is a much more sophisticated situation. So if the range of G, which is this set, does not communicate well with a domain of F, then some adjustments need to be made. I will not ask you to find the domain of function composition. Okay, this is a more involved topic. Although I think most of the problems in your text will have all real numbers as domain and range, but that's not true. That's not the case. So I will not test you potential problem domain of function composition. I will not test you on that. If there is a problem in my math lab, please bring it to class for everyone to see, and I'll explain how to determine, but I hope there is none. There is no need for you to go over that.
So we will be testing with common domain, right?
Yes, for the sum difference, yes, product. Okay. 2.7, inverse functions. If you remember when we started chapter 2, we looked at two potential